All right, so let's get started with what we were doing in the Friday lecture. We're talking about concept learning, right? So just to get refreshed with what we did. Oh, sorry. I need to zoom out a little bit. Right. So the idea was that we want to learn a concept. A concept, as we saw last time, was a way to define objects, right? And mathematically, it is a way to assign a label to data objects. So something either belongs to a concept or does not, right? And then we saw many ways to sort of say the same thing. So it's belongs to the concept or not, it's +1 or -1, 1 or 0, true or false, admits or rejects, right? So they all mean the same thing. So belongs or does not belong, and then just the same thing, we keep saying it in many ways. So it's 1 or 0, so that's another label, 1 or -1, true or false, accepts or rejects, right? So the idea is that there's a concept which is kind of a function C, and then you give it a data object which is represented in some form X, and then it can either output one of these two things, right? So if it outputs 1, we say it accepts the object as part of the concept. If it outputs 0, then we say it rejects. Yeah, so that is the idea. Now then we saw that if we know that our entire data space, right, the set that contains all the data objects, if we denote that by X, and if we can enumerate it, if it's countable, right, that means that we have a notion of the size of X. Then the number of concepts that there can be is given by 2 raised to power X, binary concepts, because it's essentially coloring things red or blue or green or red, right? So you can do that in 2 power X ways. Then we said that, hey, what if we assume that our X is nothing but a D attributes, right, or D features. So if each X is defined using D binary features, right, then we saw that the size of X, all the data points that there can be, is just 2 power D. That means that your concept space for this example implies that our concept space, and we typically denote our C, this fancy C, we use fancy C to denote our concept space, and this would be the size of C would be 2 power D, very large, right? So this is the space that contains the concept that we want to learn. So we denote it by a large circle. So this is our C, right? Now clearly, even for small values of D, this space is very large, right? And the idea behind machine learning algorithms is primarily to just search for the right answer using training data, right? But if our concept space is so large, it's very hard to do this search efficiently, right? You could pretty much enumerate all possible concepts, but in computer science, that's something that we don't do. We want to find answers which are computable, which are efficient, right? So we can write a program and something that can run in finite amount of time and not sort of take forever, right? So for that, what we do is we make some assumptions. We say that instead of assuming that C belongs to this large C, we assume that C belongs to a smaller set, and we denote it by a fancy H because we call this our hypothesis space. So we have a hypothesis, right? Our hypothesis is that the target concept belongs to a small area here. This is our hypothesis space. Okay, so that makes our job a little easier, and then we search for it. Then the training algorithm, all it does is it runs on some training data and produces the target hypothesis. We won't call it the target concept because we don't know if it is the right concept, right? So we typically denote that by H, or let's call it a learning algorithm. Learning algorithm produces H. okay? And we hope that this H is same as C, right? That's when we know that we have done the right job. But what we will see is that that's not very easy. All right. So far what we have done is we have made a simplification here, saying we are only going to look in this small space and then we are going to produce an H, right? Then we saw one particular example in which we made this hypothesis was that C is conjunctive, right? And we defined what a conjunctive is. Essentially a logical AND of a few of the feature values, right? So we assume that C is conjunctive, which means that the size of H becomes 3 power d plus 1, because if you remember it, right? So we can either have, assuming that you have all these binary values, right? So you can enumerate it and it comes out to 3 power d plus 1, right? Which is much smaller than 2 power d, right? So then we said that if this is the case, we looked at one particular algorithm called findS that was able, and we showed how it runs, and we hope that it runs in the right way. So this is just a brief recap of what we did on Friday. 6. Right, so any questions about all of this? All right, so the first thing we're going to see today is some properties of this findS algorithm. A lot of you had pointed out that it's not a very good algorithm, and I agree. But we still want to figure out why it's not good and what can be done to make it better, right? So let me switch to the slides so that we can look at the algorithm quickly. So this was that algorithm. It's called findS, right? And all you do is, as you keep getting positive examples, you keep refining your hypothesis. So you begin with the most specific hypothesis. This is the hypothesis that accepts nothing as the target concept, or accept nothing as part of the concept. And then you slowly, as you keep seeing positive examples, you keep refining it. And at the end of it, whatever you get, you stop there, right? Now the first question is, will it always learn the target concept, right? And you can easily see that it won't work. It will not, it's not guaranteed to learn the target concept. It actually depends on the training data that you get. It actually very highly depends on that. So let's look at one example. So let's say our target concept was this, right? So any tumor, we're talking about tumors here, which are defined using 5 features. So any tumor that is large and thick, this is conjunction, right? Any tumor that is large and thick is going to be, is what we call malignant, or is our concept, right? So the Mother Nature, the way Mother Nature sort of labels your tumors is by looking at this concept. But the algorithm doesn't know that, right? Now, it would get some training data, and the training data has to be consistent with this concept, right? We are assuming that everything is correct, the labeling is correct. You can see that if you get these two as your training data examples, right? Circular, large, light, smooth, thick, and oval, large, dark, irregular, thick, and both are positive or malignant, then you will see that just with these two examples, you would actually arrive at this target concept, right? Because in the first case, so you will begin with a empty concept over here, or the most specific. In this, when you get the first example, what you would do is you will just keep this as our hypothesis, right? And then in the second example, you will do a pairwise AND. This will get replaced by a question mark. This will stay as a large, question mark, large, thick, and that's it, right? So actually, just with two examples, you would learn the target concept. But it turns out that this is just pure luck, right? You can also come up with training data sets in which it would never arrive at the concept, right? For example, and we'll see that in the next slide. So for example, let's say the target concept is the same, right? And this is the training data that you get. Now, when you go home, you can work through this example, but let's quickly sort of do it here. So you have in the beginning, your hypothesis would be empty, right? Then you get this as your first training example. This is malignant. So you're going to replace your hypothesis with this. In the second case, you will do a pairwise AND. So in the second case, it will remove something. In fact, let me try to do that here. Document camera. Right. So as I said, and I'm going to use a little bit of shorthand. So this is our target, which is question mark, large, question mark, thick. Right. So in the beginning, our H is just most specific, rejects everything. Now you get the first example, which is circular, large, light, smooth, and thick, and it is malignant, which means its class is, it belongs to the concept, right? Which means that according to the algorithm, we will do a pairwise AND of this with this, and that's a special thing, and it will give us H as just this object, right? And it makes sense, right? Because this is the first object that you have seen, and all you do is you say, I'm going to call any object that looks exactly like this as malignant, nothing else. Yeah. So this is our H. Now comes the second data point: circular, large, light, irregular, and thick, and that also is malignant. So now you do a pairwise AND of this with this, and then what you get, new hypothesis, is just circular, large, light. This gets replaced by a question mark because they are not the same, and thick, right? Then the third comes, and the third one actually turns out to be a benign, or it does not belong to the concept, which means that according to the algorithm, we do not change our H. So H stays the same. Fourth one is also benign, and we don't change it, so that also stays the same, right? And let's say the fifth one is malignant. So let's say the fifth one is circular, small, light, smooth, and thick, and that's malignant. Now what you will do is you'll sort of take a pairwise AND of H with this one, and then you get H as circular, question mark, I made a mistake, right? Sorry, this is not my malignant example. My malignant example is oval, large, light, irregular, thick, okay? And that's malignant. So now when I do a pairwise AND of this with this, I get question mark, large, oh sorry, right, question mark, thick, right? And that's it. My data is done, training data. So I'd say this is my C, or this is my target concept, right? But clearly this is not my target concept. Our target concept was actually this on the top, right? So this is a little more specific. We call this more specific because it looks at more features to decide if it's a malignant tumor or not, whereas this one is a little more general, right? This one will call more instances as malignant, because if you get a new, so now let's say this is done, so training is done. Now if you get a new data instance, which is this, for just for testing, so let's say our X star new instance is right. So let's say it is anything circular, large, dark, what is it, irregular, and thick. Right, so this is our new data. What will this concept call this? Benign, right? It will call it not part of the concept, because H, so H of X star will be equal to benign or not part of the concept, because it doesn't agree on one of these things, right? Because it's a conjunction. However, if you remember our target concept C over here, this will call this object as malignant, right? So C of, so if this we call it C, so C of X star actually will be malignant, because the things that it's really interested in are correct. You see, so this is where your algorithm will make a mistake, sorry, because your output is going to call a data object benign, whereas this one is going to call it malignant. So essentially the whole point of the exercise was to show that this FIND-S algorithm does not guarantee a correct answer. It depends on what training data you get, right? So I showed you in one example, even with two data instances, you would arrive at the right answer, whereas in certain cases, even with 5 data instances, you might not get to the right answer. So it depends on the what you get. So, and then there are other issues with this algorithm as well. So for example, so what we need in a good machine learning algorithm is not just the ability to get to the right answer, but also some ability to tell us that I am not at the right answer, right? Because that would happen many times. Depending on the training data, you might not have enough data that your algorithm could converge to the right answer. But algorithms like these ones, they just give you one answer, right? And all they say is that this is the right answer. And that's a little scary, right? So we want algorithms that are a little more sort of accommodating, or at least they can give you some indication that, you know, I could not get to the right answer. So that is one bad thing about this algorithm, right? However, one thing that you might want to notice, and I might just leave it as an exercise for home, is that, and if you read the class notes, the answers are there. So it's not that much of an exercise. But the hypothesis learned by FIND-S, right, will never label a benign instance as malignant. That's kind of something that you can actually prove. So after it has done the training, right, if you get a new data object, we saw here, right, that this object was actually malignant and our answer labeled it as benign. But the converse will never happen. So if you give it a benign object, it will always call it benign. It will never call it malignant. That's just the property of this algorithm, and you can actually work it out. Let me give you some hints. So think about this. So what you will see here is the way this algorithm works, right? It starts from the most specific hypothesis, and then it keeps sort of whittling it down, right? It keeps removing some parts of that hypothesis as you get more and more training, more and more positive examples, or more and more malignant examples, which means that at any point your algorithm will always be more specific than the correct concept, right? So which means you can see here as well, right? So this was your target concept and your hypothesis is this. So it's not very different from your target concept. The difference is always going to be that it will have a few more features represented here than the target concept. That's it. So you can actually look at the algorithm and you can understand that at home. Which means that at any point, if there is a benign example or an example that does not belong to the concept, the reason it is benign is because it does not agree with any of the target concept, right? Anything. So for example, let's say, let me rewrite it. C is question mark, large, question mark, thick, right? So any benign example, right? Any benign example, if you take, so for any benign example, at least one of these will be opposite, right? That's why they will be labeled as benign by this concept, right? So you cannot have a benign example in which this is large and this is thick, because it becomes a malignant example. Either this will be small or this will be thin, or both will be different, right? So at least one will be different, which means that your H if you look at your H, which is learned by the FIND-S algorithm, that also will have these two things, and it might have few more, which means that it would also call this example as benign because this will get sort of violated for that algorithm as well. All right. So that is sort of a very quick description of that proof. But go back and you can look at the class notes as well. There will be a gradients quiz problem next week that will be fairly similar to this. So I won't go too much into that. All right. Any questions so far? Very nice. All right. So let's keep moving. I don't like this pen. Your treasure of pens here. Oh, this is what I wanted. Okay, so let's keep moving, all right? So now you understand about FindS and all its limitations, right? All I'm trying to say is that it is a very bad algorithm. So now we want to move on to algorithms which can tell us when you are, if you are at the right concept or if you're far away, right? So we are going to look at one more algorithm. It's called candidate elimination. Well, actually, we're going to look at two more algorithms. So let's first sort of define a new concept, which is called consistency. Consistency of a hypothesis with respect to a data set, all right, to a training data set. So a hypothesis H is called consistent with respect to a training data set if it correctly labels all the data, all the objects to their corresponding classes. So remember, our training data set is nothing but X and the label, right? So let's say X1, data point 1 and its label, data point 2, something with this. It's having a hard time focusing. Is it visible in the back? Fine, all right. Okay, so let's say our training data looks like this. It has some n data points, right? So this is the object and this is the label, right, which is labeled by the concept. Now, a hypothesis H is called consistent if it correctly labels all of them. So which means that H of x1 is equal to C of x1, H of x2, C of x2, and so on. Right, so that is a notion of consistency. So based on the consistency, any questions about consistency? It's a pretty simple concept, right? It's just all the correct hypotheses. So now we define this notion of a version space. So a version space, or I will write it as VS, is the set of all consistent hypotheses, all right? So let's say at any given point, right, so let's say H is your hypothesis space. So a version space is a subset of H, right? All the concepts in version space are within H as well, but all of the hypotheses in version space are consistent with your training data, okay? So that is the whole thing. So VS is a set of H such that H belongs to H and H is consistent with D, whatever your training data is. So version space is tied to a data set, right? So if I change the data set, the version space will also change. So that is just the idea. So the reason we are talking about version space is that instead of trying to learn one hypothesis, right? Instead of trying to learn that one hypothesis and claiming that this is the target concept, we are going to come up with an algorithm which will give us the version space, which means that it will give us all the hypotheses which are so far consistent with our training data set, because that's what we want, right? If it so happens that that version space contains only one hypothesis, that's perfect, because that would be our target concept. However, if it is larger, then it's also fine. At least the user knows that based on whatever training data set, right now, all of these could be correct, right? So you're shifting the responsibility to the user, right? In the same, other thing is that the target concept C will always belong to the version space, because target concept C has labeled these these points, so it will be consistent, right? The target concept cannot be inconsistent with your training data set, because that's the one that assigned these labels, right? So it's just cx1 will be equal to cx1, yeah? So that's the idea. So now let's look at an algorithm that learns the version space. So there's a very simple algorithm there, which is called list then eliminate. These people are not very creative with the naming of algorithms, but this one is just called list then eliminate. And all it does is, this algorithm, it starts in the other way. It first says that my version space is my entire hypothesis space, okay? Then as you get new training data instances, you eliminate all those hypotheses which are inconsistent with this training instance, right? So the idea is that first, this is your H, right? It contains all the hypotheses, all the conjunctive concepts essentially, if you're assuming conjunction. And then what it does is it gets a new data point, x1, and it gets its label, right? Then it takes every hypothesis here and then compares H of x1 with C of x1. So if it matches, that means that hypothesis is consistent with this data point, so it keeps it. If it's not a match, it chucks it out, right? So it eliminates. So it first lists all the possible hypotheses and then eliminates the one that are not consistent. Now a new data point would come next time, CHX2, and then it again does the same business, but with the reduced hypothesis space, right? So at the end of it, you can see that it would be left with a version space, because those will be all the hypotheses which will be consistent with all of these training data points, right? So it's a reasonable algorithm, but it turns out it's not a very efficient algorithm. Why? Because if you look at the implementation, right, if you want to implement it, what you would have to do is list all the possible hypotheses. Remember, if it's a conjunctive concept class, then we are talking about 3 power d plus 1 hypotheses, right? If d is pretty large, let's say even 10, then you're talking about a very large hypothesis space to enumerate, right? So every time what you would have to do is you have to take all of these and then check this condition for all of them, right? So it's fairly inefficient. So that's why, even though it's a reasonable algorithm in terms of how it learns the version space, it's not something that we'll look at. This is all the space that I'll give it. All right, so now we will go to a more sort of a efficient algorithm which does the same thing, which means that it is going to learn the version space, but it is going to do it in a very efficient manner. Any questions so far? List then eliminate. No fans here. Right. Okay, all right. So the first thing about talking about sort of how do we come up with efficient algorithms is to first look at this version space, all right? So if you look at a version space, so version space is just a bunch of hypotheses, right? So what we can do in a version space is we can actually arrange these hypotheses, okay? We can arrange these hypotheses based on how specific or how general they are. So remember, if you remember in our discussion last week, right? We looked at one hypothesis which looked like this, phi, right? Which was the sort of reject all. We called it reject all because it calls everything as not part of the concept, everything as a benign tumor. And then on one end, you had a accept everything hypothesis. right? So we call this the most general hypothesis because it accepts everything, and this is the most specific because it accepts 0 elements, right? So what you can do actually is you can take any hypothesis and you can put it on a scale from most general to most specific by looking at, okay, how many objects does it cover, right? So for example, a hypothesis that is like this: circular, large, I forgot the whole thing, irregular, smooth and thick maybe. So this hypothesis, it covers only one object, which is this object, right? So this would be maybe the next most specific hypothesis, and there could be many more at this level because they all sort of label one object as a positive example. On this side, you can have a hypothesis circular, question mark, question mark, question mark, question mark, and this would be slightly more general, slightly more specific than this one, right? So which means that because it's going to cover a whole lot but not these many objects as a positive example, right? So the idea is that you can do the same thing in version space as well, because version space is nothing but a set of hypotheses. So you can arrange all the hypotheses within a version space on this scale. Some would be very specific, some would be very general, and everything else would be in the middle, right? And what we will see today and maybe in the next class is that once you arrange them, right, you will see that you can ignore everything in the middle. So if once you arrange your version space in this way, so here would be most specific and here would be most general, and here will be all the hypotheses in the middle, right? So we call this the most general boundary, most specific boundary. So it turns out that we will see a theorem that we can ignore all of these hypotheses, put them on the side and only use these, and that will be enough. What we will see is that if we can learn these boundaries, that's it. We don't need to learn things in the middle. So what that does is that it significantly compresses the version space. So instead of trying to learn everything in the version space, which our favorite algorithm list and eliminate was doing, right, we will only learn the boundaries and that will be enough. And that is what the algorithm called candidate elimination does. All right, so let's see how that works. I'm going to use, oh, we had a break. Oh, that's why I'm a little off on my timing. Got it. Any questions so far? All right, so before looking at candidate elimination, I just want to introduce a couple of relationships. So we already talked about it, right? So we can define some relationships between hypotheses. We can define this relationship called more general than. So one hypothesis can be defined as more general than other one if it covers more instances than this one, right? So any hypothesis, the role of a hypothesis is that it is going to call some objects as positive or malignant and some as benign, right? Another hypothesis would be more general than this one if it covers everything that this one covers, calls everything that this calls as positive and a few more, right? So it's kind of easy to understand. The same way you can define a more specific sort of a relationship as well. So there's a more general than relationship which I have written in a pretty convoluted mathematical form, but just to understand it, it has more things. So if you talk about conjunctive hypotheses, the idea would be that if, let's say, you have a hypothesis like this: circular, large, question mark, question mark, question mark, right? So this hypothesis is going to call all objects which are circular and large as belongs to the concept. So so let's call this H1, and then H2, let's say, is circular, question mark, question mark, question mark, question mark. So this hypothesis is also going to call the same objects that this one called as part of the concept, but a few more as well, right? So that means that H2 is more general than H1, right? This is fairly easy to understand. The reason we are looking at this relationship is because that is going to help us sort of create that that ordering, right? What we will do is we will put the most specific ones on the top, something that we cannot go more specific than. Then we're going to put little less general, and the most general in the bottom, right? So that way we get this ordering of our entire version space. Right. So for example, let's look at this example, right? So there's a this data set. I think we saw this earlier as well. So you can look at these different hypotheses. They are all consistent with your training data, right? Now remember, we are talking about version space, which means that all of the hypotheses have to be consistent with the training data. That's the first sort of requirement. But what you can see is that they can be arranged in different ways, right? So for example, if I take these three consistent hypotheses, I can see that this one is the most specific among the all three, right? Because you cannot go more specific than this without becoming inconsistent. And same way, these ones are the most general that we have so far, right? So these are all that we came from these. So if you had run the list then eliminate, then these would be the hypotheses in the version space, and you can arrange them like this. So essentially what happens is that and in this case there is nothing in the middle, but you could have more in the middle as well. And what will happen in the candidate elimination algorithm is that it will only try to learn these boundary hypotheses, and everything in the middle is going to be ignored. And the reason they are going to be ignored is because of this theorem called version space representation theorem, which says that if you have any hypothesis H in the middle, right, then you don't need it, because there will always be one hypothesis on the top and one on the bottom that should be enough to represent this one. Okay, so there's the expression of this theorem, and we're going to look at the proof in the next class. The idea is that if you take any hypothesis H in the version space, there will always be one hypothesis in the most general set of on the boundary on the top. We call that capital G, uppercase G, and the most specific boundary here. So you'll always find a pair which would sort of satisfy this. And because it satisfies this, it means that we don't need it really. We can so if you have a new object, right, X, then if you want to figure out, okay, what will H of X be, it is enough to see what will G of X be and what will S of X be, which means that you don't really need that H to make the new prediction, right? And that's what you need these hypotheses for anyway. So because of this theorem, we can come up with a more efficient algorithm, and we'll look at that algorithm and the proof of this theorem on well, we have a little more time. Oh, I see, this clock is a little off. What is the time? Oh, we have 6 minutes. All right, yeah, we can do a little more. Sorry about that. Any questions so far? You're all very quiet today, huh? You're all still shocked by the result of the game yesterday. Like, oh, what happened? How could that happen? All right. So what does version space representation theorem say? What it says is that if you can arrange your version space, right, into a form that you have the most specific hypothesis here and the most general here. Okay, so S is a set of hypotheses such that there cannot be any hypothesis which is more specific than these. Okay, so that's just a definition. And G is all the hypotheses in your version space such that nothing can be more general than this, right? So if you can arrange this, then if you take any H here, okay, then the theorem says that there will be an S, lowercase s, that belongs to here, and one G that belongs to just G, such that H will be more specific than this G and more general than this S, right? So that is sort of the definition of this theorem, that any hypothesis in the middle is going to be covered or be bounded by these two on these boundaries. Okay, so the first so there are two questions here. What is this true or not? So that is the proof that we will do next time. But the next question is, why is this useful, right? Why are we concerned about this theorem at all? So I'm going to answer the second question first. The reason we are concerned about this is that once this is true, once we have established that this is true, it means that we don't need H at all. We don't need to learn H as long as we have learned everything here. Because if a new object X comes, right, or X star, something that we have not seen in our training data set, arrives, then we can look at S of X star and we can look at G of X star, and that will tell us what H of X star was going to be, because H is more specific, more general than S, right, and H is more specific than G. So as long as we know these two things, okay, and next class I'll go a little more into that. So the way to think about it is that what is the most specific hypothesis, right?